We're going to introduce the concept of confidence intervals, which is based on the idea of estimation, using data from a sample, a statistic from a sample, to make a statement about where the truth is, the population parameter. Let's say, for example, we wanted to estimate what percent of the diet is composed of fat. So we know that there are some guidelines. At the time I'm recording this, the guidelines are something between 20 and 35% of your calories should come from fat. How could we see if that's the truth, if that's what people are actually doing? Well, we could take a random sample. We could calculate the diet and see what percent of what percent of calories are coming from fat. And let's say, and we take a sample of, let's see here, 167 women. And the mean is something like 36.5%. What do we think is going on in the population? Do you think the true population parameter is actually exactly 36.5%? Probably not. Had we taken a different sample, we get a different number. Why? It's random. The mean is a random variable. It bounces around due to chance alone, due to the vagaries of random sampling, chance. And the question is then, how much does it bounce around? And we quantify this a little bit with the standard error of the mean. Standard error means how much does it move? And once we know how much that mean moves around by chance alone, then we are able to do something like this. Let's take our 36.5% and add some sort of fudge factor, some sort of uncertainty, some sort of estimate around that number to say what's going on in the population. This is a really weird concept, but it's not complicated. But let's think about it like this. If you spent the rest of your life repeatedly taking samples of the same size over and over and over again, calculating the mean, plotting out those means, eventually you would get a distribution of those means. Now, luckily, you don't have to do that. We know what this will look like. It will look like a normal distribution. The middle of it will be around mu, whatever the truth is, the population parameter. But you won't get the same mean every single time. Sometimes, just by chance, you might get means that are a little bit higher. Sometimes they will be a little bit lower, but most of the time they will be somewhat around the average. This is the building up of a distribution. And we can describe this distribution with a measure of spread called the standard error of the mean. This is driven again by two things. How spread out is the population itself, the standard deviation of the population, and what is the size of our sample. So you can think about the standard error of the mean in a way of this is so confusing to say. The standard error of the mean is the standard deviation of the sample means, the standard deviation of the sample means. So again, if you randomly took samples again and again and again, how spread out would they be? What would the noise be? It can be described by the SEM. Now, I said the SEM can be thought of as a standard deviation, and that is interesting because this is normal, this curve. And in a normal curve, we know that most, 68%, most of the points will be within one standard deviation of the mean. Now here, if this measure, the SEM, if that's our standard deviation, our measure of spread, we know that most of the means, 68%, will be within one SEM of the truth. So if you go out and take a sample, you know that most of the time it will be within one SEM of what's actually going on in the population. And what's the SEM? Well, the SEM you can derive from this. What's the spread and what's your sample size? Now, carrying on from that, look at the second bullet point. 95% of the means will be within 2 SEM. So that means almost all of these hypothetical means will be within 2 SEM. And you can see that on the curve. Here's our 2 SEM. And you see about 95% of those points. This is very fancy. About 95% of those points are within those 2 SEM. And then, of course, you would say, 99% of the means are literally, dude, almost all of them are within 3 SEM. So this is the truth. This is what happens if you don't believe me, you can just spend the rest of your life doing this. Go take 10 light bulbs, put them in your mirror, sit there and see how long they last, calculate X bar, and then go to the store, take another random sample and do it again. Eventually you'll get a curve like this, and eventually you will come up and you will say, all right, Tyler, these 3 things are true. That's what happens. That's the sampling distribution of means. But in the real world, you do a study one time. That's why it's called a study, one time. So when we take one mean, how does this apply? What does this mean? Well, we talked very early that the idea that a distribution like this can be thought of as not only the actual things that you see, but also can be thought of in terms of probability. And when you combine those two facts, this slide becomes very interesting because I just need to change some words. So if I go here, if we think of that exact same curve in terms of probability, now we can write these statements. If you take one mean, if you take one mean, in other words, that's a sample, right? That's a study. There's a 68% chance that your mean will be in here. And there's a 95% chance that your mean will be in here. And there's a 99% chance that your mean will be in here. I think it's pretty obvious or intuitive based on the last slide. If you just understand and appreciate the fact that this curve, it can be thought of in terms of probability. All right, so let's combine that first graphic with this graphic, and now let's actually do this idea of estimation. So let's say that when we take our mean, X bar, and this statistic, a guide to the unknown, where is that population parameter? Let's put an interval around it. Now, I'm going to do a little bit of a reveal and tell you that the interval we're going to use, at least to start with, is this interval. We're going to take X bar, and then we're going to add 2 times the SEM, and we're going to take X bar, and we're going to subtract 2 times the SEM, and we'll get some sort of interval that looks like this. Here's our X bar, and then we just add this little fudge factor around it. Something like that. It's an interval. And we're going to write it with the idea we'll take X bar, and then in parentheses, we'll see, we're going to put whatever our interval is. So let's just play with this for a little bit and see how this works. So imagine that you actually knew the truth. And again, you don't. That's why we're doing this. But let's say that the truth is something like this. And here's the population parameter, mu. And if you randomly go out and take a sample, let's say you get an X bar of right here. This is your first sample or your first friend. Now, if you take that X bar, and if you go and you really say, I know that that X bar is not the truth, but the truth is probably somewhere around it, then you can make an interval and say the truth is probably somewhere around it. And again, we'll do X bar plus or minus 2 times, that's a typo, X bar plus or minus 2 times the SEM. Now notice that interval that you would make, you would go around saying, hey, I got a mean of this, but the truth is somewhere between these 2 things. Notice what that interval includes. It includes the truth. So you wouldn't be wrong when you go around and say, I think the truth is somewhere between these 2 bounds. Let's say you take another sample, X bar here. Again, you make that interval. Or let's say this isn't you. Let's say this is your friend Kevin or your colleagues in California. Now, they get a different mean than you, just randomly, but the interval, they overlap a lot. They're consistent with a lot of the same truths. And it happens that this interval also contains the truth. Let's say you got a sample and you take a mean that's a little bit lower. Again, in real life, you only take one sample. But these are potential manifestations of the truth. Or sorry, potential manifestations of the mean, right? You wake up, you take a mean, it's going to be different every day. So you see that when you make intervals, sometimes they will catch the truth, but sometimes they won't. This interval right here, you got a low mean when you did this study. Why? Just randomly. And when you make that interval, you won't catch the truth. Now we're going to see, and we're going to talk a lot about, you don't know whether you caught the truth or not. But when we build up something like this, we're going to see something really interesting. This is the same idea. Let's take random samples. Here's Kevin. Kevin does a study. He makes an X bar. He makes an estimate, or what's called a confidence interval around it. Notice that his interval would actually catch this truth. And what we're going to see is that anytime you would get an X bar that's within these bounds, anytime you get an X bar that's within those bounds, that interval, which is mean plus or minus 2 times SEM, that interval will catch the truth. So again, this is confusing, but anytime your interval or anytime your X bar falls in this bound, this little interval will catch the truth. So we can ask this question. Oh, good. So anytime you fall in that bound, your confidence interval will catch the truth. This is known as the confidence interval, and we call this the 95% CI. And as we're going to see, and if you've taken statistics before, you know that that 2, that multiplier, and that 95% are linked. But let's look at this statement a little bit more. Anytime your mean falls in that interval, then you catch the truth. So how often does that happen? Well, that interval, this mean 1 SEM, 2 SEM, how often will your X bar fall in that interval? Well, 95% of the time. And how often then will your confidence interval contain the truth? 95% of the time. And when you understand this, and it'll take 3 or 4 times before you really get it, you'll realize that combining these elements of random sampling, combine this knowledge of what the sampling distribution of means will look like, and the really important fact that a study is just a random instance, it's just a random number, then you get to see how these confidence intervals work. So the confidence interval is going to be our main tool for estimation, a guide to the unknown. Take our sample, couch it with some sort of uncertainty, and say we are now 95% confident that the truth is somewhere in that bound. And we'll work on this with some examples in the next video.